Anyway, thanks for okay. Thanks for having me here. My name is Franco Vazza. I'm a researcher at the University of Bologna. I'm supposed to I was supposed to close this session about the theory of everything. I hope you haven't been waiting for the final answer because I have no clue, but at least at the end you will get coffee in the worst case. So, the core topic of my research is to study the cosmic web, and I'm trying to address the issue of missing baryons and magnetogenesis, but towards the end of the talk I will move into unexplored territory for me, so I will step into measurement of information and complexity, and finally even try to compare with the human neuronal network, which is not my main topic of research. Next we have a movie that, okay, oh, fantastic, okay. I could just stay here for the entire 15 minutes looking at my moves. Anyway, so on the left we have the distribution of baryons. We can trace through X-ray, so they are pinpointing cluster of galaxies or group of galaxies, and what we see here is the odd gas, while on the right we see the entire distribution of gas, which is in the cosmic web as we can simulate it. So what we can see in X-ray observation is a tiny fraction, like a few percent of the total content of baryons in the universe. Observing galaxies, we can add a bit more to this budget, but the total, like more than 90% of baryons in the universe, are spread into the cosmic web, which is something which is really elusive to observations. Can we? Okay. And studying the distribution of matter of baryons in the cosmic web is crucial for at least a couple of very important questions. One is indeed to locate and measure how cosmic baryons are spread at very large scale. We know they should be there because they were there at the epoch probed by the cosmic microwave background, but somehow they are missing from our observation as we probe into the low redshift universe. Another big mystery, which is also attached to this big enterprise you might have heard of, the square kilometer array. Can we dim the light a bit, please? Is the origin of cosmic magnetism. We have strong evidence on magnetic fields outside radio galaxies on scales of several tens of kiloparsec, but recent radio observations in, a couple of decades are consistently showing the existence of magnetic fields on scales of 2 or 3 megaparsec, which is roughly 10 million light years. They are well detached from galaxies. They are just probing the existence of relativistic particles and magnetic fields at very large distance. We don't have a clear idea of why they are there, and we can think at least about two possible different scenarios. In one case, those are the remnant of the magnetic fields ejected by galaxies. On the other end, they can be the remnant of a generation of magnetic fields during inflation or baryogenesis at very, very high redshift. And the idea also behind the starting grant I was assigned from the European Research Council last year is that if we can observe systematically radio emission at very large scales in the universe, we can start killing theories and decide which of these two opposite theory is the correct one, because at some point the signature from cosmic magnetic fields at the scale of filaments would show radically different signatures depending on which of the two theories is correct. Now we move into that's an observation that is combining more or less the three most important proxies we have for cosmic matter and kinds of energy. So we have galaxies here that are mostly traced in the dark matter potential or the total matter potential well of a galaxy cluster. Then we have hot X-ray emitting gas here in purple, observed with Chandra. And then here we have this green, very elongated structure, again from side to side, roughly 10 million light years across, which is the acceleration site of relativistic electrons, we think, and those are marking the conversion and dissipation of kinetic energy of gas entering into the cluster potential well, which is shocked and can convert huge fraction of energy into heat and also into the acceleration of particles. Like we are speaking of 10 to the 45 ergs per second of energy dissipation in these mergers. And this, by the way, has been observed with the LOFAR, low-frequency radio telescope, whose core is in the Netherlands. That's an observational fact, but of course with galaxy cluster we can only see a still frame of their evolution that takes place over giga-years, and now we move to a movie, which is instead another simulation which is trying to simulate. Can we display it full? Okay, so we have now a high-resolution simulation. On the left-hand side, we see the assembly of gas matter over time, and here on the right, we have the pattern of shock waves we can measure in the same simulation in post-processing, and we can measure how shock waves are been injected in the center, they start being weak because the medium is hot, and as they move outwards, they become, sorry for this, they become stronger and they can dissipate more energy. And we can already see visually that the pattern associated to the accretion of matter, even if they might be elusive to telescope observation, are supposed to be extremely complex. Now we move on. So at some point I got interested into information theory, which is not, again, my core topic, and I wanted to ask myself, can we quantify how much complex is the formation of such a complex object like a galaxy cluster? And this was already subject of a paper in Monthly Notices last year. So a very small introduction on, so the Shannon information has been already introduced several times, so we'll just move to the Kolmogorov algorithmic complexity, which is a possible approach in which you want to quantify how many bits of information do we need to perfectly reproduce a certain sequence of data without losing any information. So if you're speaking of a cosmological simulation, basically that's the number of bits we need to store the entire output of a simulation somewhere. This is not entirely satisfactory from the physical point of view, because what we are most interested in is the statistical complexity of the parent population for which the cosmological simulation is coming from. We are not interested into the byte-wise values of certain variables, but to the complexity associated to the statistical behavior of it. You can think the problem in terms of, if you want to describe 20 tosses of coins in a lossless way, you need exactly to store the result of every single toss of coin, which will require you something like 2 to the 20 bits, while instead the statistical outcome of that is extremely simple. And we want to have the same approach on simulation. We want to quantify how statistically complex they are, and we can compare in this way different simulations, even if they are at the byte-wise level different, statistically maybe they share the same complexity. So on a practical point of view, you can simulate the evolution of a galaxy cluster, and basically here I'm using an Eulerian grid-based approach in which we simulate the evolution of thermal energy, we have kinetic energy associated to the gas, even magnetic fields. I'm not showing here dark matter. That's a boring lambda CDM model in concordance cosmology. You simulate the evolution, then you can access back the data stream among cells in the simulation, and an algorithm for doing that is, for example, we can partition the different energy states of each of these fields into a number of bins, and then we can measure from the data stream the metrics of possible transitions across states. So we can measure how the energy in a cell is going to transition at the next time step and to move into something else. If the evolution is simple, we might expect that all cells at a given energy bins are all transitioning to the same other energy bins. If the evolution is complex, we can see a spread in the trajectories of those cells in energy space. And by the way, this is very interesting because there is no physics here. We are just analyzing the digital output of the simulation, but we are not imposing any physical prior on what's really happening in the simulation, even if, of course, we are the god of such universes, so we also know what are the physical law behind it. So after that, we can just map in space and time a distribution of probabilities associated with the transitions of each different cell, and then we can compute the Shannon information associated to the whole realization. This is what we can get at the end. Can we dim again the light, please? That's a cut through the simulation, now showing the maps of complexity in bits associated to the thermal energy, the kinetic energy, the magnetic energy. I'm sorry, you don't see probably very well the patterns, but the general idea is that magnetic complexity is spread all throughout the cluster, because what we see here is dynamo amplification, and dynamo is something which is volume filling and is able to convert kinetic energy into magnetic energy in the center of the cluster following this turbulent accretion pattern, while the complexity associated to the thermal and the kinetic part is more peaking in the outer parts where we have shocks. And we can see that even if we draw this kind of phase diagram in which we plot here the statistical complexity in bits per cell versus the density. So the center of cluster would be here and the periphery would be here. And this is also very important to design future simulation, because we can, and we are already designing algorithms in which we can teach the code to refine somewhere the grid in the simulation as a function of the complexity the data stream is showing. So without any prior guesses about what shocks or what turbulence should like in the simulation, we can tell the code just look through the flow of data and then decide where you have to refine. And also, I don't have enough time to go through it, but there is another important proxy, which is called the block entropy, which is like a time analysis of the sequences of energy states we can have somewhere in the simulation, and we can analyze it through basically symbolic analysis, like you would do to analyze how much complex are the sequences of words in a book, for example. And we can compare different realization of the same simulation, also introducing what simulators call radiative cooling and AGN feedback. And we can, for example, track as a function of time the epochs in which the energy output of AGNs can introduce complexity in the simulation. So the energy output of AGNs might be gone by the end of the simulation. We are here, a redshift 0, but its complexity output, so the introduction of complex evolutionary pattern, can be recorded fairly well with this technique. And combining the first thing I presented, the statistical complexity, to the second one, the entropy gain in this case, we can also study the emergence of complex patterns. So the ratio of these two quantities is meant to represent basically the ratio of how much we can predict from the data stream here and how much difficult it is to obtain a prediction. And we can repeat the same analysis at different levels of resolution in the simulation, so we can coarse grain our data across a narrow range of scales here, and we can compute this figure of merit. When this is the maximum, this is marking where making predictions becomes more efficient and where we have the emergence of complex pattern in our simulation. And this scale is of the order of 100 kiloparsec, which is a bit larger than the scale of galaxies, and is a typical clustering scale for example, the width of filaments, and is also correlating well with the size of clumps, shocks, and turbulent eddies we can measure in the conventional way in our simulation. If we go to, if you can extrapolate to extremely small scales, when we can, in principle, study the dynamics of simple protons and electrons, all this is gone. It's the same process in which we go from the dynamics of particles collision to hydrodynamics. So the complexity is arising here. Then, recently I've been extrapolating the same approach now to simulate an entire universe. And again, can we please show the full? Okay. Now we will see the evolution of thermal and magnetic energy in a slice, forming galaxy clusters here and filaments, and these two structures are going to merge. So we can also study the complexity associated to the formation of an entire universe, which is still not as big as the entire observable universe, but if we have a fairly large cosmological box, then we can extrapolate it to the scale of the entire observable universe, and we can repeat the same algorithmic analysis and statistical complexity analysis, processing the entire data stream of the simulation. So we go back, that was the last movie. So that would be just a simple projection to the entire box. Okay, usual stuff, we have gas density, gas temperature, and now we are going to overlay the complexity pattern, which are loosely following, of course, the structure of the cosmic web, but they are not concentrating in the center of galaxy cluster, because complexity, according to my filtering technique, is maximum when we have accretion of matter and we have this abrupt transition among energy states. And we can now measure it as a function of redshift here for different realization of a cosmic box to have a sense of the cosmic variance. And we can estimate how many bytes of information we need to statistically reproduce the evolution of the universe, grain on scales of 100 kiloparsec. And we get this number. And also we get this very interesting abrupt increase between redshift 3 and 2 that correspond to the formation of most of halos we have in the simulation. And this is giving us, if we extrapolate to the entire size of the observable universe, also taking into account cosmological factors, etc., we have that inside the radius of 15 co-moving gigaparsec, we need around 8 petabytes of data to statistically characterize how much complex is the evolution of the cosmic web. And now we move into the embarrassing part, meaning I'm not so much responsible of this, because here I joined forces with a friend of mine who also happened to be a neurosurgeon and a neuroscientist at the University Polyclinic in Modena. And there we try to compare, to cross-compare our fields of analysis. So we have here a simple sketch for the morphology of the cosmic web, in which we can identify filaments, voids, and cluster of galaxies. And something similar can be done if you take a cut through the human brain. And if we compute numbers, very roughly speaking, in one case here we can extrapolate from direct simulation from our group or other groups, and in this case we have to rely much more on the literature and extrapolate a lot, but we find that the number of neurons in the human brain is in the same ballpark on the number of halos, considering an halo something which has a mass larger than 10 to the 8 solar masses in the entire visible universe, 10 to the 10, 10 to the 11. The number of filaments in the universe is more or less of the same order of filaments we can find in the human brain, and the number of filaments per halo is more uncertain, and I could find only numbers which are going from 10 to 10 to the 3 dendrites per neuron in the case of the human brain. But what's more relevant is that we try to post-process with the same quantitative analysis a digital slice through one of my simulations to a digital slice, to a real slice for micrometer thick through both the cerebellum and the neuronal cortex of the real human brain. And with techniques, I have no idea what they are actually meaning, but they are standard laboratory techniques. And then we try to analyze it using a technique which is rather standard in cosmology. The cosmologists in the room probably would recognize it. So we analyze the power spectrum of fluctuation, which means we could analyze the density fluctuation that we have to digitalize, of course, in both cases, and renormalize. We transform that in Fourier space, and we could measure the correlation as a function of scale, or better, of an inverse scale between these density fluctuation, between this density fluctuation as a function of scale. That's a rather standard technique you can use in cosmology to study the cosmic web, or the cosmic microwave background, or the clustering of galaxies in galactic surveys. And this is what we found. So here we are comparing. In the case of the cosmic web, we have some scatter due to cosmic variance, because we could simulate different slices. And here we have the signature associated to either the cerebellum or the cortex. As you might see, we had to rearrange the two kinds of scales, because there is a 10 to the 27 difference in scales. But once we renormalize the quantities and we just focus on the patterns, they are, I would say, remarkably similar, considering we are speaking of such different phenomena. And what's also very interesting, they don't show a simple power law. They show the signature of a difference in power law shape here. And we compared it to other digitalized version of other natural phenomena we could somehow gather together. So, for example, density fluctuation in clouds, or tree branches of simulated plasma turbulence, or simulated water turbulence. And in all these cases, they pretty much show some sort of fractal behavior, which is not the same of what we find both in the cosmic web or in the human brain. So similar, but not a fractal, I would say. And finally, relying on the numbers I was just suggesting for the statistical analysis of the cosmic web here, if we want to compare with, again, huge extrapolation that have been recently made in the literature coming from different paths. So one is a sort of extrapolation of this estimate of 4.7 bits per synapses that we can extrapolate for the number of synapses in the brain. Or if you go to the ERC proposal of the Human Brain Project, you will find similar numbers. So intriguingly enough, we have that if we compare the total statistical information, we need to explain the evolution of the cosmic web grain on scale of 100 kiloparsec. Let me remind that again. If we compare it to the total memory capacity of the human brain, interestingly enough, we fall in the same ballpark. So probably it's, okay, probably that's an unnecessary remark in this audience, but this appeared already in a popular article, and then a lot of crazy comments appear, like we are not claiming the universe is a global brain or a computer. All of this is nonsense. We are just saying that we can extract just from the data in a quantitative way possible measurements of the complexity associated to the two systems, and we can try to basically bring the two of them to the same ground in which we can analyze both of them with similar techniques like network analysis, complexity analysis, but of course their dynamics and their evolution is entirely different. So those are my conclusions. So the cosmic web, analyzed with standard astrophysical analysis, is carrying a lot of crucial information about the origin of cosmic magnetic fields on large scales, and also about the fate of cosmic baryons at low redshift. And the evolution we can simulate of those structures is complex, and is complex in a quantitative sense based on information theory. And we find that this complexity is mostly associated to accretion patterns that are always present in the outer parts of galaxy cluster, were present when halos basically started to assembling, and they are emergent on scales of a few tens or hundreds of kiloparsec. And following this analysis, we can attempt to compare the complexity of the cosmic web and on the human brain using similar techniques. And we find that their total information content, grain on particular scales, is very similar. And as a concluding remark, you can think of that, depending on what you like more, you can imagine that you might use an entire human brain to codify the clustering of galaxies in the universe, in the entire observable universe on a specific scale, or vice versa. You can imagine that the entire observable universe, just using the clustering information of galaxies and their evolution, might be enough to codify the entire memory of one person, not the entire Earth, not billions of people, but just roughly speaking, 1 or 2 persons. So that's the end of my talks. Thanks for your attention.
Thank you, Franco. Are there questions?
I have a question. Franco, thank you. I'm just wondering, a few slides back you were talking, you picked out that neither the human brain nor the cosmos seems to have a fractal quality.
Mm-hmm.
I'm wondering what the foundation of that was in the context of fractals. Have you looked at that in the mathematical sense, or are you just talking about something else?
So a fractal in the power spectrum should give you, as far as I know, a constant power law, and in this particular plot, which is a two-dimensional one, should give you something like k to the minus 2, which is something like we see here. So the measurement suggests it's not. I know that in cosmology, since a couple of decades, is a kind of established fact, because you don't have a scale-free, scale-invariant formation of structures, because, for example, the free streaming of dark matter particles, etc., imposes some particular scales in the universe. So you don't expect this power law to go forever. In the case of the human brain, I cannot say. I'm not an expert there. So here I'm just reporting what we can measure in this.
So you're saying it's not a power law on the basis?
It's not an unbroken power law.
Oh, okay.
There are some features, and there are some large-scale features that are correlating with the size of the observable universe, etc., and the horizon of particles.
Other questions? Yeah, there are one back there. Marco has another way.
So, recently, there was a paper that is looking in a topological way at the brain, in a way that we actually have been looking also recently at the cosmic web, where you basically look at the connectivity of
Yeah.
the various structures. And the result of that brain research project is that the human brain is actually far more complex than the cosmic web.
Okay.
We're talking about topological dimension in the order of 11.
Uh-huh.
And this is based on a new topological concept of persistent topology and Betty numbers.
Yeah.
And so, in that sense, how do you get to the conclusion that it must be the same? I think it's actually rather different.
I'm not entirely aware of this research, but I know you can, of course, it's a network. You can use the connectivity, and you can reduce all the complexity to counting how many connections are between the different nodes in the cosmic web, etc. That's a different sort of analysis. I cannot tell if this is more powerful than this one. This one relies on dynamics. So we are studying how the network is changing as a function of time. So we can study how the energy is flowing, say, across scales and across time. The other kind of analysis is analysis of connectivity. I'm not an expert, so I can imagine that depending on a particular analysis, you can get different answer, and what's the right one. I'm here to learn, basically. I have no idea. For sure, the analysis of connectivity is far more complex in a sense than this one, because there is an intermediate step. Well, you have to somehow tessellate and derive all the connections between the different halos in the cosmic web and the different nodes, etc. Here, we just rely on basically a cell-wise analysis of how energy is changing.
Right. In terms of fractal description, what you have described in terms of entropy, isn't that just one of the dimensions of the multifractal spectrum? Because, there's a distinction between fractal and the more complex issue of multifractals. And multifractals are basically scaling of the various, or of the basic moments of the counts. And so this is one of them, but there is, of course, a whole sequence.
That I have to study, definitely. I don't know the answer to that.
we have one more question over there. Dean, if you could throw the cue.
Yeah, somewhat along the lines over there. I was wondering actually, in the extreme you can have very isolated structures in an empty space, or you can have a very dense structures in a sort of, you get a random distribution. So I'm wondering in both cases, the fact that you get a fairly similar distribution, is this representative of the fact that you have a sort of ordering and connectivity in both the brain and the cosmic web, that is very, it underlies a very general principle and not something very fundamental. And the only, although it is what you say, that structure is not fractal, but in fact it's, when you look at most of network type things or connectivity, you will find a similar type of dependence.
Mm-hmm. No, I fully agree with that. So the hope was exactly to establish the fact that despite the difference in physics and origin and everything, there might be a lot of shared methods we can use to characterize both. If you analyze the clustering of cosmic matter, you have the problem that you are dealing with density contrasts that are far larger than what you can have in the human brain. Of course, we are speaking of orders of magnitude in difference in clustering. So what you call isolated or cluster can have differences in the local environment by 100 or 1000 difference in overdensity. But globally speaking, yes, we are dealing with two networks that are somehow associating and clustering and distributing information across scale and filling also the volume they're occupying in a rather similar way, I would say.
Okay, one more question there.
I think one other major difference I see between the two networks is that in the human brain, the dendrites, some of them anyway, can be very long and they can be connecting two parts of the brain that are very far from each other.
Mm-hmm.
I don't think that really happens in the cosmic wave, right? And that may be partly because how they evolve. And those different parts are supposed to be related to different kinds of memories that we have.
I fully, if I understood the question, I think I fully agree. So the next step was also to measure the how the universe and how the brain more or less are computing. So what's the computing power, and what you get, roughly speaking, is that the exchange of information that the universe can have done on those scales in gigayears, I mean, since its start, is corresponding to what the human brain can do in less than 1 second, more or less. So we also had the misfortunate title in a popular article like "The Universe as a Baby Brain," that again attracted a lot of crackpots and stuff. But no, yeah, definitely the finite speed of energy and, I mean, information exchange across those scales is another very important difference between the two.